Hi everyone, we are here to discuss about the applications of radar in remote sensing. Now, what is radar? Radar is the acronym for radio detection and ranging, and it is a detection system that uses radio waves or microwaves to determine the distance or range, angle or velocity of objects. It can be used to detect aircraft, ships, spacecrafts, guided missiles, motor vehicles, weather formations, and terrain. Now, this is the block diagram of a radar system. We have a transmitter, we have a receiver, then a display control system, and an antenna which works same as which works both as a transmitter and a receiver of the signals. Now, a radar system consists of a transmitter producing electromagnetic waves in the radio or microwave domain, a transmitting antenna, a receiving antenna. Often, the same antenna is used for transmitting and receiving, and a receiver to processor and a receiver and a processor to determine the properties of the objects. How the radar system works. The electromagnetic signal induced by the transmitter unit is radiated into space by a radar antenna. Whenever the electromagnetic wave is transmitted by the system, then it reflects or re-radiates some of its parts of experiencing variation in the conductivity of the medium. The variation in the conductivity arises due to the presence of an object either stationary or moving, thereby producing an echo. The radar system receives the echo by the help of the antenna. The analysis of this signal gives the information about the object. Now we talk about various radar instruments that have been used in various space experiments. There are scatterometers, radio altimeters, a long track scanning radiometers, global ozone monitoring experiment, microwave sounder, and synthetic aperture radar. These are only some of the devices that has been used in the remote sensing arena. Now, wind scatterometers. The scatterometers are active remote sensing instruments that are used by low Earth orbiting satellites for deriving wind direction and speed from the roughness of the sea. What it does is it measures the roughness of the sea by some method, and from that roughness we can derive wind direction and speed of the wind. Then it has been become increasingly important tool for monitoring climate forecasting, weather, and studying the atmospheric ocean interactions. Now this is the result of a wind scatterometer. The map shows displays the ocean surface winds at 10 meter on the 20th July 2000 from the ERS2 scatterometer. Now, radar altimeter. Radar altimeter is designed to make the accurate measurements of the satellite's height above the sea surface, which is then converted into the sea surface height above the reference ellipsoid. When the altimeter takes the height measurement, it measures the height contributed by height contributed by many different types of phenomena, from the underlying marine geoid through a large scale of general circulation of the oceans to mesoscale eddies 100 kilometer across. In addition to highly precise height measurements, the altimeter makes measurements of the heights of waves that appear in its footprint and the surface wind speed. Then applications of radio altimeters. They are measuring the marine geoid. Information can be extracted by the altimeter data to provide the maps of average sea surface topology, the marine geoid. It is used in geoid determination. Altimetry aids in revealing location of ocean floors such as faults, trenches, spreading zones, sea mounts, and hotspots. Then measuring sea state. The radar altimeter also measures the height of waves that appear within the footprint, and the wind speed is at the surface. Near real time measurements of the altimeters are assimilated operationally into wave models to provide wave forecast essential for the optimization of range of marine operations. Then measuring topography of oceans. Ocean topography can be easily measured directly and monitored for change using ARS radio altimeter. Along with the data from the other similar instruments, the information can be assimilated into ocean circulation models, which transforms the satellite surface image information into a three-dimensional description of ocean current and transportation. This is a global bathymetric prediction of the sea surface elevation measured by the ERS-1 radio sensing system. Now, the along track scanning radiometers or ATSR. The remote sensing data from ERS to ATSR2 allows the monitoring of Agriculture fires and wildfire distributions on a global scale and in near real time. All hotspots with a temperature higher than 312 Kelvin at night are precisely located, and data from ATSR sensors also used for volcano monitoring applications and measuring ocean skin temperatures. This is the result of the an alone track scanning radiometer, which shows the soil moisture or lack of vegetation in different colors. Now, a global ozone monitoring experiment. Atmospheric ocean and nitrogen dioxide global monitoring have been going on since GOME products became available. Additional applications could stem from ongoing scientific studies. GOME's data can also be used for retrieving other trace gases relevant to the ozone chemistry, as well as the atmospheric constituents and climate variables like clouds, aerosols, and soil index, all of which are crucial for assessing the climate change. This is the this is the GOME experiment result of the ozone cover of the region around above the Antarctica. We can see that the mapping of the ozone density has been mapped in the Dosman unit. Then microwave sounders. The ERS-2 microwave sounder is being used to monitor the Antarctic ice cycle. Mapping of the radiometric properties of ice shelf, which has a slower time evolution than the atmosphere and the ocean, provides a valuable input for the understanding of the growth, decay, and dynamics of the ice sheets. This in turn is fundamental to the understanding of environmental and climate changes. This is the microwave sound result of monitoring Antarctic ice cycle. Ocean appears as blue and the sea as yellow. Sea ice as yellow. Now, synthetic aperture radar. Synthetic aperture radar is a technique for creating high-resolution imagery of the surface over the area of surface being observed. These images represent the backscattered microwave energy, and characteristics of which depends on the properties of the surface, such as slopes, roughness, humidity, and textural inhomogeneities, dielectric constants, etc. SAR has become a valuable remote sensing tool for both military and civil applications. Military SAR applications include intelligence gathering, battlefield reconnaissance, and weapon guidance. Civilian applications include topography mapping, geology and mining, oil spills monitoring, then sea ice monitoring, oceanography, agricultural classification and assessment, land use monitoring, and planetary or celestial investigations. So, applications of SAR on the ocean, most of the man-made illegal or accidental spills are highly visible on the radar images. Ships can be detected and tracked from their wakes. Natural seepage from oil deposits can also be observed, providing hint for the oil industries. Ocean waves and their direction of displacement can be derived. Then at high latitude, SIR data is very useful in regional ice monitoring. On the land, the ability of SAR to penetrate a cloud cover makes it particularly valuable in frequently cloud areas such as tropics. Some geological or geomorphological features are enhanced in radar images. SAR data can be used to georeference other satellite imagery to high precision and to update thematic maps. And then used in flood mapping to derive elevation models, etc. are the applications of this SAR data on the land. This is a satellite imagery versus SAR imagery. Then a verified oil spill image from SAR. And remote sensing applications in Earth environment. Past climatic conditions studied by analyzing ice cores, sea or lake sediments, shoreline movements, tree pollen, etc. Numerical experiments are also run in which global circulation models are used to explore the possible climatic changes related to, for example, the Earth axis oscillations. Knowledge of past climate can help in predicting the future climate. A fundamental role in the determination of the Earth climate is played by the solar radiation reaching the Earth, affecting the ground surface energy balance. The radiation spectrum at the Earth is strongly influenced by atmospheric constituents. Not only the amount of radiation, but also the spectral distribution is so crucial. Then coastal zone monitoring. The first one is the detection of oil spills, monitoring illegal discharge and is an important component in ensuring compliance with the marine protection legislation and general protection of coastal environment. Traditionally, this service uses airborne patrols which are expensive and provide often only patchy coverage. Fast delivery SAR products are proving to be of great value in optimization of airborne surveillance resources. Due to the large area they can image at any time, any on time. Size, location, and disbursement of the oil spill can be conveniently determined using this type of imagery. This is the Sea Empress 147,000 ton super tanker run around the rocks in the south of Wales on the evening of February 15th, 1996. 7 days later, radar stars captured this image, clearly delineating the remaining oil slick. Size, location, disbursement of the oil spill can be conveniently determined using this type of imagery. The spill appears on the image as black tones. Now, shallow water battery mapping. SIR imagery acquired under the suitable ocean currents and surface ocean wind conditions allows the bottom topography for an area of tidal sea to be visualized. This imagery is then used to infer bathymetric using numerical inversion procedure. Combining conventional echo sounder data from a survey track with SAR imagery can shorten survey times considerably, producing a bathymetric map of the required accuracy, thus representing a major saving cost. This is a shallow water bathymetry model derived from ALOS AVNIR2 multispectral data over the GBR study area. Now, the ship detection in coastal regions. Knowledge of the whereabouts and activities of ships in coastal regions is useful to a range of government and law enforcement agencies, such as those concerned with enforcing legislation regarding the fishing activities and exclusive economic zones, and environmental protection agencies support pollution control. The information is also used to coast guard the use of both in search and rescue operations and in law enforcement activities to supplement land-based coastal surveillance radars, which has a maximum range under 1,100 km. It has been recognized that satellite-based radar has the ability to detect and monitor vessel traffic. Due to the nature of the radar, monitoring can take place through cloud cover and at night, thus providing advantages over the optical data. Monitoring the common agricultural policy in European Union. The agricultural monitoring can be done using the earth observation data from a SAR value, from a satellite, from a radio, from a radar data. This is the radar sat image shows the agriculture region in state of Washington. Circular features near the bottom of the image are created by central uh, private irrigation system. The brighter circles could be indicate either the presence of vegetation or the increase in amount of moisture in the fields. A bit to the north, there is an area characterized by rectangular field patterns. The brighter fields are vegetated while the darker are bare. To the east, striking dendritic changes of patterns are also visible. Now, tropical forest monitoring. SAR data can be used as a unique data source and in conjunction with other remote sensor data to map the forest damage. The encroachment of agriculture onto a forested area unsuitable for development and in general to provide inventories of timber areas. In natural resource exploitation, in order to make large scale surveying of as yet explored regions as cost effective as possible, exploration of managers are looking to new methods such as the use of satellite data. The identification mapping of terrestrial structures related to the hydrocarbon and mineral deposits is the key to many individual applications within geology, such as general geological mapping to the mineral deposits location. Then mapping and updation. The words mapping industries are currently experiencing a rapid technological and organizational change. Increasingly, information is needed to digital formats, enabling the sophisticated analysis of the undertaken, producing products such as digital terrain models over the land, over which land covers information can then be typed. Digital data are also of great value in the rapidly expanding market for GIS, which are now being used extensively to integrate data from different sources for land management and monitoring and planning. Now, marine environment hazardous risks. Earth observation data from ER satellites helpful assessment of the forewarning of range of forewarning of a range of environmental risks hazards in the marine environment, whether the natural or man-made. Radar data helps in the forecasting sea states for offshore operations and marine engineering. The study of climatology of marine areas is offshore operations. Then it is also used in sea ice monitoring and navigation in Arctic operations. Now, natural disasters, ground-based measurements of volcano deformation can be used to assess the eruptive hazard, but require the costly installation and maintenance of instrument network. It has been demonstrated that spaceborne radar interferometry can be used to monitor long-term volcano deformation. The deformation associated with the large data eruption of Mount Etna was measured and interpreted using INSAR technique for the first time on a volcano. Earthquakes and landslides. Magnitude 7.3 landmass earthquake of 20th June 1992 ruptured over 82 kilometers along the complex fault system in the Mojave Desert of California. The landmass earthquake sequence provided ideal test case for radar interferometry because it shows its shallow depth produces spectral surface rupture and arid areas less than 3 months after ERS-1 satellite began to occurring radar images into 35-day orbital cycle. With 20 fringes in the shape of a crushed butterfly, the first earthquake infragram illustrates the cosmic formation fields over a million pixels. This shows the land earthquake. Now, floods, bad weather and therefore denser clouds causally accompany floods, and therefore optical sensors cannot be used for monitoring purposes. Radar satellites, however, can penetrate the cloud cover with the microwave and thus deliver valuable information for future planning and prevention. Now, hurricanes. Unlike optical sensors, radar can penetrate to all weather conditions, including clouds and rain, having an all-weather image capable of making radar unique bees being able to detect and effects of hurricanes on the ocean surface with the high spatial resolution. The hurricane features visible in the radarsat imagery are imprint of the hurricanes on the ocean surface roughness. In the radsat imagery, the eye of the hurricane appears as darker than the surrounding area because the wind speed at the center of the hurricane is lower. Then the case studies. The first case study is the radar remote sensing for the delineation of forest cover maps and the detection of reforestation done by C. Thiel and et al. The paper illustrates the capabilities of L-band synthetic aperture radar for forest cover mapping and delineation of deforestation. The assessment was carried out at 5 test sites. The L-band satellite data over the temperature and boreal forest, when classified after image segmentation, allows the detection of forest felling with an accuracy of 90% and creation of forest cover maps with similar accuracies. The procedure for mapping reforestation areas exploits the time series range of SR images taken from the period of 1990 to 1998 during the year in which JERS was operational. Two different approaches were developed. The first detects the forest cover separately for each JERS scene, while the second takes all scenes into account simultaneously. The images are classified under forest, non-forest, and deforested areas. The overall accuracy of the derived forest cover map is about 90%. Now this is the images classified image. Right side shows the classified image and left side shows the radar image. Left side shows the radar image. Now case study 2, urban object detection from C-band synthetic aperture radar satellite images through simulating filter properties by Deepak Kumar. This shows the methodology that has been chosen by them. Now the present work aims and utilizes central SAR data Data studies. The work uses C-band SAR dataset acquired from Sentinel-1AB sensor and the Google Earth dataset to validate recognized objects. The C-band sympathetic aperture radar images acquired from the Sentinel-1AB satellites offers a free dual polarization, vertical transmit, vertical receive, vertical transmit, horizontal receive are the different configurations, resolutions and band combinations in their corresponding ascending and descending orbits. It presents a distinct evaluation of urban and urban features, detection and identification approaches with spectral filters at pixel level to understand the performance of each approach. Each approaches with a set of dual pole SAR images and corresponding Google Map imagery for the ground truth verification. The experiment results revealed that the proposed technique works well over the traditional methods of in terms of accuracy and precision. This is a case study 3. Accuracy of permafrost frost region coherence variation in the Koihai Tibet plateau with high resolution TMSRX image by Sejinga Sang. The studies analyzes variation of coherence of QTP area over the first time for the first time with the high resolution SAR image acquired from the June 2014 to August 2016. The coherence variation of typical ground target was obtained and analyzed because of the effects of active layer freezing thawing. Coherence maps generated in the Beluhi permafrost area exhibit seasonal variation. Furthermore, a temporal decorrelation method model determines determined by a linear temporal decorrelation component plus a seasonal periodic decorrelation component and a constant component have been proposed. The time series coherence maps of study areas were developed. The experimental research shows that railway and highway hold high coherence during the whole observation with the maximum coherence value greater than 0.8. Those high coherence points could be used for the deformation monitoring of the Q2B using the time series in SAR. On the mountain slope, barren and alpine meadow areas, the coherence shows the obvious seasonal variation. A new temporal decorrelation model is proposed herein for permafrost areas. Most typical ground targets fit in the temporal decorrelation models determined by a linear temporal decorrelation component and the seasonal periodic decorrelation component and a constant component. In this study, railway and highway can hold high coherence even when the temporal baseline over several years with X-band SAR data. The time series coherence maps of study area for SMG is given. Now the reference. Thank you.